In Chapter 2, we're going to be talking about acids and bases. Oddly enough, if you've had Chem 3A, you may have covered some of this. If you've only had Chem 1A, this material is generally covered in Chem 1B, and so you might have to pay a little bit closer attention. But in general, you know, acids are things with H on them, and bases tend to be things that are lacking the H, like OH minus, for example. Now, if we look at the Bronsted-Lowry definition, this is maybe one that you've heard before. In the Bronsted-Lowry definition, we base whether or not something's an acid, whether or not it donates a proton or accepts a proton. So what's a proton? Well, proton is just H plus, and it's sort of got this name. It's because if you think about the Lewis dot structure for hydrogen, it looks like this. So if you remove the electron from it, you'll have something like this. You remove the electron. This is H plus. So what is H plus? Well, that's just the nucleus of hydrogen, and so that's just a proton, a single proton. So acids are said to be proton donors. So things like HCl. But in the Bronsted-Lowry definition, anything with a hydrogen can act as a proton donor. And so, in general, anything could be an acid. Now, of course, some of the hydrogens aren't very acidic, and so we're going to have to learn some of the rules about, like, how do you know whether or not the hydrogen is going to be acidic enough. Now, for things that you learned as acids like HCl, HNO3, H2SO4, those things will generally always be acids because they have the hydrogen to donate. Bases, then, in the Bronsted-Lowry definition, are proton acceptors. Now, here's the tricky thing about a proton acceptor. Proton acceptor can be anything with a lone pair of electrons. And you may not have thought about acids and bases in that way, but if you think about OH minus, right? So we can draw the Lewis structure for OH minus. What does OH minus have on it? Well, if you remember and have been practicing your Lewis structures, you should come up with that fairly quickly. These are the acceptors of the proton. That is, you can add an H plus to that, and what you end up with is H2O. So anything with the pair of electrons can be a base. Anything with a hydrogen can be the acid. So before we move on, I'd like to talk a little bit about donors and acceptors and this idea of acid strength. So when we have an acid, we can write its reaction like we have here on this middle line that's down here. Okay, so what we have is HA. A just stands for anion. And remember, every time that you have an acid, the proton will come off and that'll leave you with a negatively charged anion. And then we have water that's here, and then we have A minus. Now, think about what this means. This had a hydrogen. That is, this guy here had the hydrogen, and he lost it over here. So what that means is that this is the acid, and this is the base, because if you look at its structure, all right, it's H2O here, and it picked up the H here, H plus here, so it's H3O plus now. So we have, in terms of our Bronsted-Lowry acid-base definition, we have the acid, which is HA, we have water in this case, which is the base, and we have on the other side the anion created by the acid. So this is known as the conjugate base. And this is known as the conjugate acid. Now, if you think about what that actually means then, right, we call this the conjugate base. Now, the conjugate base always comes from the acid, but you'll notice that this arrow has two directions on it. It has a forward direction and a backwards direction. What this is implying is that the reaction goes both directions, that this is what is known as a reversible reaction. So when you're going backwards, that is, you're following this arrow, you notice that this A minus that's over here picks up. That is, when it goes back to the other side to become the acid again, it picks up a hydrogen as it goes from here to here, which means this is A minus is acting as a base, and H3O plus, which is the conjugate acid of water, is donating the hydrogen back to the A minus to produce the acid. Okay, so this is that Bronsted-Lowry definition. We have an acid and a base, and a conjugate base and a conjugate acid. Now, we can write something called an equilibrium constant. Now, it's not that important that you get hung up about writing equilibrium constants in this class. But if you notice that those are the products. And down here, we have the reactants. And the brackets refer to the molarity or concentration. So what we have in this letter here, Ka, this is known as the acid equilibrium constant. We have a way to measure or quantify the strength of the acid. So we can quantify acid strength. Now, how does that work? Well, let's say HA is a really strong acid, which means it's going to give a lot of hydrogen up, right? A lot of the molecules will give hydrogens up to the water, which means the concentration of A minus and H3O plus will be large. On the other hand, because the HA is donating hydrogens, its concentration will go down. Now think about what Ka is. If Ka for a strong acid would be large, it's larger for strong acids because the numerator, the top part of the equation, is going to be big and the bottom part of the equation is going to be small. Now the opposite is true too. If an acid is weak, that is, doesn't give up a lot of hydrogen ions, then Ka will be small. So it would be nice if we could just leave it at that, but what we like to do is look at something called the pKa, and this requires a little bit of knowledge of logarithms. Logs, that's this guy up here. The pKa is the negative log, that's this, the negative log of the Ka value. So let's see how this works. Let me go ahead and describe to you in the next slide how taking the negative log of a number translates into the pKa. So here's a table of Kas and pKas. Now you're not going to have to be doing a lot of converting back and forth, so I'm not going to show you how to go from pKa to Ka, but that involves the inverse log. Now if you remember, pKa is the negative log of the Ka. So what I'm going to do is calculate the negative log of 1.3 times 10 to the minus 1. So I'm going to type in 1.3, and then on your computer you have to type E, which is kind of not cool, but that's the way it works. And then, so that's the times 10 to the notation. And we're going to say 1, change sign, and then we're going to take the log. You'll notice this is negative 0.88 0.886. So in terms of the pKa equation, what that becomes is 1.886. Sorry, it becomes positive 0.886. So in other words, this becomes 0, oops, let me get a pen out, 0.886, because we're looking at the negative pKa as being the negative log of the Ka value. So the log of the Ka was minus 0.886, and then when you take the negative of that, that gives you your pKa. So let me very quickly, I'm going to pause my recording, and I will write the rest of the values in so you can see them. So there are the rest of the values. You'll notice that if you take 1.3 times 10 to the minus 1, you get 0.886. 5.6 times 10 to the minus 4, you get 3.25. If you have 1.3 times 10 to the minus 6, you'll end up with 5.886. And 5.6 times 10 to the minus 9 gives you 8.25. So there's a couple things in general that you should be noticing about these numbers. One, the big picture, right? Smaller number, smaller Ka, larger pKa. And that's because of that negative sign in the calculation. Now, the other thing to notice in general is that you'll notice if it's 5.6, this is 2.5, this is 5.6, and this is 2.5. And the only difference is the 3 and the 9 and the 8. And it turns out the 3 and the 8 are related closely to this exponent. It's the power of 10 which most closely represents that number. And then you'll notice this is 0.886 for 1.3, and this is for 1.3 times 10 to the minus 6. There's a 0.886 down here too. So this part of the number on this side represents the actual number. It's the digits in the number. And this side represents the power of 10. But in general, what the most important thing to recognize is large values for Ka or larger values for Ka give you smaller values for pKa. And again, on the top, this would be stronger acid, and these would be weaker down here. Okay? Based on what we've talked about in the pKa in the previous section. This slide sort of summarizes what we just were talking about. When we talk about acid strength and acid equilibrium, we're primarily talking about Ka, and that's the reaction of the acid with water to produce its conjugate base and hydronium ion. For strong acids, Ka values are large. So you notice here this is like 10 to the second. And for weak acid, Ka values can be very small. Now in water, these values, about the smallest you can get is about 10 to the minus 14. But in non-aqueous solutions, these values can be like 10 to the minus 25, 10 to the minus 55, things like that. So you'll notice the scale, strong acids, pKa's, will be negative. And for weak acids, again, larger numbers, larger positive numbers represent weaker acids. So I've got a reaction for HCl and water to form chloride and hydronium ion. If you look at the pKa values I gave you, you'll notice that because the pK of HCl is lower than that of hydronium, HCl is a stronger acid than hydronium ion. Now, the donor is HCl. That is, the hydrogen is pushed onto the water, and that means this is my acid. This is my base. This is my conjugate base. I wrote conjugate over here so I could avoid writing it. And then this is my conjugate acid. Right. Now, how do you know which way the equilibrium is going to be favored? Like, is this going to be favored towards the product, or is it going to be favored towards the reactant? And the simple answer is the stronger acid will push the equilibrium towards the weaker acid. In other words, HCl is a stronger acid, so it's able to push the hydrogen to the H2O. So if you think about like a volleyball match and the hydrogen ion is the volleyball, the stronger team generally wins. And in equilibrium terms, the ball ends up on the side of the weaker acid more often than it does on the stronger acid. Sometimes we'll write equilibrium arrows that look like this to show that the equilibrium is favoring the product side. Now, again, the stronger acid is HCl, and the stronger base then is H2O, because H2O was more likely to accept the proton than a Cl minus is. There's a general principle that comes out of this, is that if an acid is strong, its conjugate base is weak. And the opposite is also true. If an acid is weak, its conjugate base is strong. So to put that into practice, here's a question about conjugate base strength. Which is the stronger base, F minus or CH3O minus? So what we do is we look at the pKa's for HF. HF is 3.2, and for CH3OH, what we find is that the CH3OH is the weaker acid. What that means, though, is F minus is the weaker base, and CH3O is the stronger base. So if you're looking at this equilibrium and trying to determine, like, does this equilibrium favor product or reactant, what we'll find is that the stronger base is here and the weaker base is here. And just like for the acid, when the stronger base or the stronger acid will, just like we find for acids, the stronger acid will push the equilibrium to the side of the weaker acid. The stronger base will do the same thing. So this equilibrium is really something like that, where, let's see. Yeah, this equilibrium is really like that, where the product or the reactants are more favored than the products. This is the stronger base. Now, if you look at it in terms of the acids, HF is a stronger acid than CH3O minus. So you could have also done it from that perspective, that the HF would push the equilibrium towards the reactant side, which tells me that I drew this wrong, like this. Something like that. Okay? Hope that wasn't too confusing. Again, you can always text me or send me an email to get clarification. Another skill that you need to have is to be able to predict which substance in a reaction is going to be the acid. The simple way to do that is to look at the pKa values, and the stronger acid of the two substances in a reaction will be acting as the proton donor, and the other substance will be the proton acceptor. So, for example, we have hydrochloric acid. It has a very low pKa. It's a very strong acid. And then we have water, and water has a relatively high pKa. Remember, high pKa's are weaker acids and low pKa's are stronger acids. So that means HCl in this mixture would be the substance behaving as an acid. The next thing you have to be able to do is predict what the products are. So take a moment, you can pause the video, and then try to write out the products of HCl and H2O, where HCl is acting as the acid and H2O is acting as the base. So here we have the reaction HCl plus H2O, where HCl acts as the acid. Remember, the hydrogen chloride, the HCl, will be the acid, so that means it donates a proton to the H2O, and then when you look at the product side, what you find is that the Cl has lost a proton and the H2O has picked up a proton to produce the hydronium ion. So what I want you to do now is take a look at the next two reactants and try to predict which one will be the acid and which one will be the base. And you can pause the video and do that and then restart it, and I'll show you the answer. So before we write the reaction, first just remember that H2O is the stronger acid of the two substances. Remember, the lower pK is the acid. And so that means it'll be the proton donor, which means, if you look at the reaction, the NH3 will accept a proton from the H2O to produce ammonium ion and hydroxide ion. I did cover this slide briefly before, but what you want to be able to do next is, once you've determined which one's the acid or which one is acting as the acid and which one's acting as the base, you want to be able to predict whether the equilibrium is going to favor more towards the product side, that is, produce more products, or stay on the reactant side and not react as far. And in order to do that, what you need to do is you need to look at the pKa of the product acid, and you compare the acid strengths for the two. And so if you look at this particular reaction, this is acetic acid, and the acetic acid is going to react with NH3, ammonia, and then it's going to be, it's the stronger of the two acids. So, it's the weaker of the two acids. So the acetic acid will donate a hydrogen to the NH3 to produce the ammonium ions. Now, what we do is we look at the acid strength, 4.8 versus 9.4. So we have the acid, right? Remember, this is the acid. This is the conjugate acid of our base. And we compare their strengths, and the stronger of the two acids will determine in which way the equilibrium is pushed. So when you see this arrow that's drawn like this, somebody's actually taken a look at the pKa's and determined that the reaction will be very product favored in this case. You can see the same thing for this reaction of ethyl alcohol, and then we'll get into the naming of these things later, and methylamine, and the methyl alcohol is the stronger of the two acids on the left hand side, so it will behave as the acid. It's the donor, and so as a result it loses a proton, and then it makes the methyl ammonium ion. Now again, you need to know a little bit about pKa's, but this pKa is 10.7. This one is 15.9, and you can predict which way the equilibrium is going to be because this is the stronger and this is the weaker. So the equilibrium, when you look at that arrow, favors the reaction staying on the left-hand side of the reaction arrow and mostly being in reactant form rather than going over to products completely. So you might be wondering how I know what these values are. So this is going to be a practice question. And here are the approximate values for the pKa's for the different substances that will be formed. This represents an ammonium ion on an alkyl group on a CH3 group. And you notice that the pKa's I have are 36, 15, and 10. I pulled those numbers from the section 2.3 in the textbook of the edition that we're using. It's on page 37 where you find the information, and also in table 2.1. I would strongly recommend that you work on becoming very familiar with those values. On an exam, I'll probably give you the same tables so you don't have to memorize them, but just so you know that if you continue on in organic chemistry, you'll probably have to have those values memorized. So this is what I want you to do. It says predict which substance will behave as the acid. So you'll be looking at the two acids in the reaction and seeing what their pKa's are on the reactant side, and then write the product of the acid-base reaction. And then what I want you to do is look at this arrow and see how you should be drawing it. If it should be more towards the product or more towards the reactant. So I'm going to pause the video. I'm going to go ahead and give you a chance to write that out, and then I'll put the solution up on the screen. So the first thing that you should be doing is looking at the pKa's of the two reactants, 36 and 15. So methanol, this is methyl alcohol with the pK of 15, that's going to be the donor. And you notice how, to help myself out, I went ahead and wrote the pKa's underneath here. So I know that the methyl alcohol will be the donor for the amine, and so this proton will get transferred over to there. Remember, it carries a positive charge, and so that proton carries a positive charge. So then I'll end up with this methyl ammonium ion, and then I'll have, it's called methoxide ion. Now, in terms of labeling, you don't really need to do this for this part, but this is the base, this is the acid, this is the conjugate acid, and this is a conjugate base. This is what we had talked about earlier. Now, in terms of determining the equilibrium position, what you need to do is you need to look at the pKa's of the acids. And so that's why I had you determine like which was the conjugate acid, which was the conjugate base. And so what you need to have is this pKa down here. That's about 10. Okay. Now, you'll notice that 10 is the stronger acid of the two, so that means the way this arrow should actually be drawn is it should be drawn longer on the bottom. That is, it's going to be favoring towards the reactant side, and then a smaller one at the top. So what I'd like to do next is make a distinction between two quantities that you often hear in acid-base discussions. One of them is pKa, which we've been talking about. pKa is related to how strong an acid is. And the other one is pH. And pH is something we associate with acidic and basic solutions. So to give a little background, when you have an acid, and in this case I just called it HA. By the way, I finally remembered how to make a pointer show up. And H2O is the base. Then what happens is the acid donates, and so it becomes A minus, and then the water accepts, and so it becomes H3O plus. This is the hydronium ion. When we talk about pH, what we're actually talking about is we're talking about something related to the concentration of hydronium. So if you remember from your Gen Chem, acids produce hydronium when reacting with water. And the solution acidity is based on the concentration of the hydronium. So this is hydronium, but this bracket means concentration of. So the common misconception is that pKa, if it's a really low number and it's a strong acid, will always produce an acidic solution. Now, in general, it will produce an acidic solution, but the actual amount of hydronium that produced is dependent on pKa and the concentration of the acid that's used. So I want to make sure that we sort of distinguish those two. pKa indicates how strong an acid is, but hydronium is the result of the reaction with water and the concentration and the strength of the acid. In general, stronger acids of the same concentration as weaker acids will make this pH lower, and then acids that are weaker will have higher pHs. That is, they'll be less acidic. And we'll talk about the pH scale here in just a second. So pH is calculated just like pKa. If you remember, pKa is equal to the negative log of Ka, and small values have small values of, let me say, hydronium concentration, or Ka, have large positive values. Okay, so low pK, small pK, or low Kas give you high pKa values. All right, so the pH scale, let me go to the next slide, looks something like this. And this slide may look familiar. It's very similar to the one that's used in most general chemistry texts. In the pH scale, we generally have it running from 0 to 14. We have 0 and 14. 7 is considered neutral. If you look at the kinds of things that are near pH 7, a lot of bodily fluids are near 7. So like saliva, human blood, tears, but even egg whites and seawater and milk, these are all things that are pH between about 6.5 to 7.5. You'll notice even rainfall, people think rainfall is super pure, but rain actually has a pH that's less than 6. And this is because of carbon dioxide in the air, when it reacts with water, forms carbonic acid. And so there's actually in rainwater that comes from the air some carbonic acid that naturally forms. So pH is less than 7. That's this range here. These are typically considered as acidic. And if you're thinking about in terms of magnitudes, this is more acidic. Lower pH means more acidic solutions. On the other hand, above 7, that's this range here, these are considered to be basic. And this is more basic on this end. Now, again, what this has to do with is hydronium ion concentration. So more acidic means more hydronium. And less acidic, more basic means less hydronium. Now, I don't have time to go into all the details of the exact values for this class, but if you're right at pH 7, what that actually means, let me just draw a long arrow over here. pH 7. Hydronium and hydroxide in solution are equal. And I could explain that to you individually later if you have questions, but pH 7 is considered to be neutral because hydronium and hydroxide concentrations are exactly the same. Now, so that's the pH scale. You'll notice sodium hydroxide, when it's 1 molar, gives you a pH of 14, whereas hydrochloric acid, when it's 1 molar, gives you a pH of 0. So this is basically the range of very acidic to very basic. Next, I want to take a look at how we view organic acids. So We talk about acids and bases a lot in general chemistry, and an acid, as we generally say, is anything with a hydrogen in the front. And bases are typically things like ammonia or NH3 or hydroxide, like sodium hydroxide, potassium hydroxide. The only thing that really sets organic acids apart are the presence of carbons and hydrogens. So R actually represents C's and H's. So for example, acetic acid is an organic acid. It's the simplest organic acid in my opinion. So it looks like this. We draw it like that. That is acetic acid. That's an organic acid because that R group, and the R stands for something called a radical, but you could just think of it as the rest of the molecule. The rest of the molecules are carbons and hydrogens. The most common organic acid is called a carboxylic acid. And it's either written like this or it's drawn out in its structure like it is shown here. These are moderate to weak acids. You can again find this in section 2.3, I believe, or 2.2 of your textbook. It talks a lot about strengths of acids. These are moderately weak acids with pKa's around 5. Alcohols can also be considered to be organic acids in some reactions, that is, proton donors. But they're much weaker, and we'll talk about these trends, like how do you know if it's going to be stronger or weaker. But an example of an organic an alcohol that is behaving as an organic acid would be something like this. This is propanol, like that, and it has an OH group on it, or sometimes it's drawn out like it's shown here, like I've shown it here, or it can actually be drawn out with all the bonds shown like this. It doesn't matter that much how you represent it. Now, when we want to understand how acids and bases work in organic chemistry, it is actually important to use a form that looks like this one here, where we have drawn out the bonds, and I'll show you how we use that information in our next slide. So there's a lot of information here, but I want to, but that's because everything's labeled. I just grabbed this slide from the textbook. When we are looking at the reaction of an organic acid and a base, and the way organic chemists view the reactions, remember this bond is a pair of electrons. So what ends up happening is when we say donor, really what's happening is this pair of electrons is actually, we would say, attacking the H, and because hydrogen can only form one bond, this bond breaks and these electrons go back to this oxygen. Now right now you see there's two lone pairs here, but if the bond really breaks like this, that is, something grabs the hydrogen and the electrons go back to the oxygen, what you expect to see in the product for this acid is the oxygen with 3 lone pairs now instead of 2, and it'll also have picked up a negative charge. If you think about formal charge with oxygen with 3 lone pairs, that's typically how oxygen gets a negative charge. Now the hydroxide over here is attacking and picking up this hydrogen, and so when it does that, it forms a new bond. So in essence, this pair of electrons is this bond, and this this bond becomes this pair of electrons. And the arrow, when we draw these arrows, we always start the arrow, right, on a pair of electrons. So the arrow starts on a pair of electrons. It ends up on an atom, and when it does that, it forms the new bond. When a bond breaks, we draw an arrow from the electrons that are the bond back to the atom, right, where the electrons are going to be residing on after that bond breaks. So that's why we have them over here. Now, Methanol with hydroxide will act as the acid, but if it's reacting with hydronium, then the hydronium is a stronger acid than the methanol is, and so the hydronium acts as the acid. That means it's the donor. But don't get confused when you do the arrows, because the arrows look like they're going the wrong way. But you start, what you know is, let's start with what we know. We know that we want to have a new bond, another hydrogen, on our base. So this is the base, right? Like it says underneath. This is the acid. The conjugate acid of the base, I'll just call it Ca, should have an extra proton on it. That means it needs another bond. So it needs this new bond. So the acid is donating a proton, but the base uses a pair of electrons to grab that hydrogen and form this new bond, and then this bond has to break because the hydrogen can only have one bond. This bond has to break and it has to go towards the oxygen because it can't go towards the hydrogen. That would be too many electrons for it. So then what ends up happening is on my acid, I end up making its conjugate base, which should have another pair of electrons on it, and the acid, conjugate acid, has a new bond and the proton attached to it. Now, pay close attention to the way these arrows are drawn, because this is how we keep track of all of our organic reactions and where things are attaching and where bonds are breaking. Here's another couple of examples. In this case, hydroxide is my base. That's here. And it's going to pick up the proton from the acid. And so we start with a pair of electrons and we draw it to the hydrogen. And then this bond needs to break and it has to go towards the oxygen. There'd be too many electrons for that hydrogen. So that means this pair of electrons, in essence, becomes the new bond. And then this pair of electrons, which is that bond, comes back to the oxygen it was attached to. Now, let's take one more look at another reactions, and we'll move on and talk about some organic bases, in particular amine bases. But we have an example here, an interesting example. This is acetic acid, and this is hydronium ion. And it turns out hydronium is more acidic than acetic acid. The pKa of hydronium is around -2. I mean, that's a pretty round number, but it's about -2. But acetic acid is only about 4 to 5. Acetic acid is like 4.7. So the result is this is more acidic than acetic acid, which is weird because you think of acetic acid as an acid. And so the hydronium becomes the proton donor. In this case, the electrons then come from the double bonded oxygen and attach to the hydrogen, and then this bond has to break because the hydrogen can only have one bond again, and then the electrons have to go towards the oxygen because the hydrogen can't accommodate any more electrons. This means that this pair of electrons becomes this new pair, this bond here, and that the other pair of electrons, that is this pair of electrons, goes to form another lone pair on the oxygen. In this case, it forms water. So again, very consistent. Pair of electrons from the base attacks the hydrogen. Attack is the word we use, by the way. Attacks the hydrogen on the acid. And then the acid has to form that new bond and release, the hydrogen has to form that new bond and release the electrons back to where the atom they were attached to originally. And those form a new bond and actually a new pair, lone pair on an atom. There was one more thing that I wanted to talk. Oh, sorry about that. I hit the mic. There was one more thing that I wanted to briefly mention. You'll notice that this arrow that's here is favoring the reactant side, and sometimes it's difficult to know like which side the arrow is going to be at if you don't have the pKa values. Now, if you had the pKa values, I think you would be able to predict that. pKa of the protonated acetic acid is like -7, and again, hydronium's like -2, like -1.7. And so you could have predicted it from that. But one of the interesting just observations is that if you take something that you believe it normally acts as an acid and you put a proton on it, it becomes much more acidic. And so you could have predicted, knowing that acids that get protonated become much more acidic, you could have predicted that the reaction would have probably been towards the left-hand side. So what I'd like to talk about next is amine bases. Remember, a base is anything that in the Bronsted-Lowry theory is anything that has a lone pair and can accept a proton. So amines fall in that category. Amines are nitrogens with a lone pair and hydrogens or carbons attached to it. So this pair of electrons can attack the hydrogen on, for example, hydronium, and it can act as the acid. And that means you're going to form a new bond here. That's the new bond that you see. And then you're going to form another lone pair on the acid, which is going to be one of these lone pairs here. So again, highlighting, right? This bond is breaking, forms this lone pair, and then this bond is going to form from that pair of electrons, okay? That bond is formed from the pair of electrons on the nitrogen. Again, keeping track of charges, because the hydrogen is carrying the positive charge, whatever picks up the hydrogen becomes more positively charged, and whatever had the hydrogen becomes more negatively charged. Now, you could also illustrate an acid-base reaction between an amine and hydroxide ion. The lone pair on the oxygen, it attacks the hydrogen to form the new bond. And then the lone pair between the nitrogen and the oxygen, that is the nitrogen and the hydrogen, has to go back to the nitrogen, forming another lone pair. So in other words, this becomes that. And again, this is neutral, but it picked up the pair of electrons. It lost the hydrogen, so it has a negative charge, and so it becomes more negative. And then the hydroxide picked up the hydrogen, became more positive to form water, which has no charge. Just a quick survey. Amines can be deprotonated or protonated. As acids, amines have pKs that are fairly high. Ammonia is 36, but methylamine is 40. Diethylamine would even be higher than that, but these are basically from 35 to 40. That's really all you need to remember. And then protonated amines can act as acids, and their pKas. Again, if you pick up a hydrogen ion, that is, you go from NH2 to NH3+, you become more acidic, and so you'll notice that the protonated amines pKa's 10.7 and 11. These are much more acidic than the straight amines. Protonated alcohols can be protonated, and so can carboxylic acids. I maybe had that one a little wrong. I said the protonated acetic acid was -7, but it's actually -6 according to your text. But protonated alcohols are -2. Protonated methyl alcohol, this is ethyl alcohol. Methyl alcohol is -2.5. We were talking about some of these values earlier. It would be good to know ballpark ranges. If you look at the table that's in your book in the section I referred to earlier, those are the kinds of values that I will be giving you. Another important topic in organic chemistry is understanding how the solution pH can be used to change the structure of an acid or a base. So again, here's acetic acid. pKa I have written here as 4.8. When you put acetic acid in water, you get a reaction of plus, oops, put it back to the pen, plus H2O, right? You form CH3, C double bond O, O minus, plus, oh, it's supposed to be a minus. I think I made that into a plus somehow. Minus, plus, H3O plus. So the acetic acid is the donor and the water is the acceptor. Now you'll notice this is the hydronium. This is what is related to the pH. If I make a solution very strongly acidic, in other words, and really what I need to do is if I make the pH less than the pKa value, and this is the important part of one of the important things about the pKa value. But if I make the solution more acidic than the strength of the acid, that's the way to think about this, then the acid will be mostly in this form. That is, it'll be in its protonated form. So that's what this statement up here means. If the pH is less than the pKa, that is, the solution is more acidic than the acid's strength, then the structure stays in its protonated form. And this applies to both protonated amines that can behave as acids and to acids like weak acids like carboxylic acids. In solution, this is how we determine what the structures of a lot of different important organic compounds will be in solution, and that helps us to predict their properties. So taking, for example, this is cysteine, the amino acid, and I've written out the pKa values for you, okay? And you'll notice that the pKa of this is called a thiol group. It is 8.2, and so if the pH is less than 8.2, it stays in its protonated form, that it has the hydrogen. If the pH if you're looking at the amino end of the amino acid, its pKa is 10.3. So if the pH is less than the pKa of 10.3, then this stays in the protonated form. And then this is the carboxylic acid. So when we talk about amino acids, it has an amine end and it also has a carboxylic acid end. Oops, excuse me. So this carboxylic acid end has a pKa of 2, and we haven't talked about this, but it has to do with the presence of these other groups that are on here. But as a result, if the pH is below 2, it stays protonated, but if it's above 2, then it's deprotonated. So what is this structure going to be, right, at physiological pH? Physiological pH is around 7 to 7.4. So what we can do is we can say, okay, well, at 7.4, right, and pKa is 8.2. I know the solution's more acidic than the pKa, so it stays protonated. 10.3, all right, is, again, the pH is less than the pK, so that one is protonated. But then look at this one. This is 2.0. So now the pH is higher than the pKa, so it will be deprotonated. So this one ends up deprotonated. The result is when you draw the structure for the amino acid, you have the sulfur when it actually has 2 lone pairs if you're keeping track of that stuff, just like we were doing Lewis structures. There's a carbon and a hydrogen. The amine end is still protonated. You can write it as NH3 plus or H3N plus. It's the same, they just swapped it around. And then double bonded oxygen, but this one will be deprotonated. So That means it'll lose the hydrogen, and I'm going to draw all the lone pairs in now, and gain a pair of electrons, and so it'll have a negative charge. In biology, you may have learned the word Zwitter ion, that it has both positive and negative charges. This is generally true for amino acids at pH 7.4, but it's not universally true. There's some amino acids that will have either be more positively or more negatively charged, depending on what the pH of the solution is. So if you're at physiological pH, you'll have one structure, but if you make it more acidic, you'll have a different structure, or more basic, you'll have a different structure. And we take advantage of those things when we do things like electrophoresis and separating and analyzing different kinds of amino acids. The last section in the chapter deals with determining the acid strength or relative strength of acids based on their structure. What we talk about in other chemistry classes is that acid strength really depends on how stable the anion is that is produced by the acid. So, for example, if you have HCl and you put it with water, H2O, then what you'll end up with is H3O plus, or you could put Cl minus first, and Cl minus. It's the stability of the Cl minus that determines how strong the acid is. The more stable the Cl minus is, the stronger the acid will be, because the Cl can be off by itself without being attached to a hydrogen. So then the question is, and we're just in general call this the anions, we'll just say A minus. So what is it about the anion that makes the acid stronger? And there's a very good book by Klein. If you want to get it, it's Organic Chemistry as a Second Language. There's 2 books, and he talks about how he teaches his students to determine acid strength based on the structure of the anion. And the first thing that he has them look at is atom. The second thing is resonance. We talked about that earlier. Induction is a new term, and then orbital hybridization is the fourth thing. And he refers to this as REO. And these are all the things that you would check to determine whether or not is an acid stronger or weaker. So when we're looking at the atom, we're looking at 2 things. We're looking at electronegativity, or size. And along the period, left to right, we'll talk about this, it's the electronegativity, and along the group, it's the size. Okay, I think I have that switched around there, don't I? More electronegative, that's on the period, and this is on the group. And I'll fix that in the slides, so you'll see that in the slides. Resonance, if an anion has resonance, it'll be more stable, and that will cause the acid, or allow the acid to be stronger. Induction has to do with electronegativity. We'll talk about that again. We'll cover that later. And then orbital has to do with hybridization. And sp hybridized atoms. Remember, we talked about that from chapter 1. Sp hybridized atoms, atoms that are bonded to only have 2 electron groups on the central atom. Those tend to be more acidic, and sp3 tends to be less acidic. So let's quickly talk about trends on the period that is going left to right. You'll notice what I have is carbon, nitrogen, oxygen, and fluorine. And if you look at your periodic table, you'll notice that these elements are left to right on the periodic table next to each other. Fluorine is the most electronegative. And so when it becomes an anion, that is, it becomes F minus, like this, right? It's going to be the most stable, because if you remember, fluorine brings the electron, is smaller as a result of its strong nuclear charge, that is, the positive charge of its nucleus, and stabilizes electrons. So fluorine, which is smaller, has a more positively charged nucleus, and on the period, what that results in is a more stable anion. So when you're looking at acid strengths, then we go down here, right? When they're nearly the same size, the strongest acid is the most electronegative, has the most electronegative atom. So fluorine is more electronegative than oxygen, so HF is stronger than H2O. Oxygen's more electronegative than nitrogen, so H2O is stronger than NH3. And then CH4 is the weakest because carbon has the lowest electronegativity of all these groups. If we're talking about the conjugate base, and this is another important concept, the strongest acids have the most stable anions, and so what that causes them to be, because they don't need to have the hydrogen attached, causes them to be the most stable bases. So the strongest base would be CH3 minus, and the weakest base of this group would be F minus. And this goes along with that saying that I brought up before, the stronger the acid, the weaker its conjugate base. In terms of stability, CH3 minus, because it doesn't have as much positive charge in its nucleus, is the least stable or strongest base. That is, it wants to pick up that extra proton. So this sort of explains why alcohols are stronger acids than amines, because when you look at CH3OH, that's methyl alcohol, versus methylamine, what we find is that the oxygen is more electronegative than the nitrogen, and so that causes the alcohol to be much stronger acid than the amine. If you remember back to when we defined these values for pKa's, these are orders of magnitude in difference, and so alcohols are roughly 25 orders of magnitude stronger acids than amines. It is also true, and I mentioned this before, if you protonate something, if you add an H plus to it, it makes it a stronger acid, but the trend is still true because the oxygen is more electronegative than the nitrogen, right? The protonated alcohol is a stronger acid than the protonated amine. If you remember, the protonated alcohols have pKa's of around minus 2-ish, and then these have pKa's of about 10. And so minus 2 versus 10, these are still much stronger acids than the amines. And those are the values. Let's go on. Now, if we're looking at trends along a group, so this is still the second half of the A of ARIO, right? We have, if you're looking at these atoms on the periodic table, fluorine is at the top of the halogens, then chlorine, and then bromine and iodine. And if you think about what this trend is for radius, iodine is the largest. Now, what we talked about before is how the nuclear charge was important in determining the strength. But large ions, that is I minus, for example, iodine, are able to spread that negative charge out around its big surface, and as a result, as a hydrogen ion comes up to it, it doesn't feel the same charge density that a hydrogen ion would feel coming up to a fluorine. Because remember, they have the same charge, but in fluorine, all that charge is concentrated in a much smaller volume. The result is that when you're looking on a group and you're looking at atom size, HI has the most stable anion, and so is the strongest acid, and HF is the smallest anion. Fluoride is the smallest anion, and as a result is the weakest acid in that group of the halogens. Here are some examples of pKa values just so you can see. CH4, this has been measured several times, I think, recently. It's somewhere between 55 and 60. NH3 is around 36, H2O is 15, and this is 3.2. Again, this is a stronger acid than this is. That is, HF is a stronger acid than CH4. Going left to right, that trend is electronegativity going this way. It has to do with the electronegativity. And then when you're looking at the trend going in this direction, it has to do with the size and the ability for the anion to disperse the charge. Now you'll notice this is -10. That's a very strong acid, and 3.2 again for HF. So getting stronger going this way because the charge can be spread out on the surface better. And so this, when you're going along this way, this has to do with radius and surface area that the charge spreads across on the atom. Resonance is also an important factor in determining the acid strength. Now, if you remember when we were talking about resonance structures, that you could draw, for example, for acetic acid, you could draw two resonance structures. The result is the negative charge that's on this oxygen partially spends its time on this oxygen, and as a result there's less negative charge density because the surface area of these where the charge is effectively larger. If you're looking at ethyl alcohol, for example, there's no resonance structures for this because there's not another oxygen here to draw another bond, double bond to, for example, like there is in acetic acid. So because there's no way for this charge to distribute, all the negative charge has to sit on the oxygen. When we look at the electrostatic potential maps, you could see how in ethyl alcohol there's a lot of negative charge localized to this oxygen. But when you look at the anion for acetic acid, acetate ion, you'll notice that the charge is spread out over both oxygen, is not nearly as charge dense. So when a hydrogen ion approaches these two structures, the hydrogen ion on the left, the one that's closest to the ethoxide ion, or the anion for ethanol, the ethoxide ion, the one that's closer to this one feels much more charge density and is more strongly attracted and will get stuck there, where the charge density here is not nearly as strong and it has less of a tendency to be attracted. The result is the delocalization of electrons causes the acid to be stronger, and then when you have localized electrons, the acids tend to be weaker. You can see that in the pKa values. You'll notice that the pKa value for ethanol is 15.9, whereas acetic acid is around 5. I mean, 4.8 is normally what's listed. But it's around 5. So if you're looking at the difference in here, that's about 11 orders of magnitude difference because of being able to delocalize electrons. The second important thing to think about is something called the inductive effect. Okay, right? It's really the third important thing to think about is something known as inductive electron withdrawal. And that you can attribute to a dipole that's created between this oxygen and carbon. Now, if you look at carbon, you look at oxygen on the periodic table, what you'll find is oxygen is further to the right, and so then you have a negative charge here and a positive charge that's here. Oh, I already drew the little dipole. Let me just draw it on the other one. A little positive charge that's here. And it turns out that this pairing of charges tends to stabilize the charge on the oxygen, and that's part of the reason why when you look at the electrostatic potential map in the previous slide, and I'll go back to that here in just a second, that sum of the charge, you'll notice that the charge is distributed towards the oxygen like it's, or on the carbon, very closely because of that positive charge that's generated that helps stabilize the negative charge on the oxygens. Well, this inductive effect can be created by actually adding other atoms to the structure of a molecule. An inductive effect is known as a through bond effect. So you notice that here I have a hydrogen. I should have probably drawn that in there. So let me go ahead and draw a hydrogen in here on the structure. I'll make this a 2. And I'll draw the hydrogen here. And what we're considering is the strength of this hydrogen here and how the strength of this hydrogen as an acid is affected by what we replace this hydrogen with. So if you put a bromine there, it's 2.86. Now, if it's just a hydrogen, it's 4.76. Now, bromine is more polarizable and more electronegative than carbon. And what that causes to happen is it causes a positive charge on this atom here. You think about electronegativity differences or a polarity there. And that positive charge through the bonds, that's what they're showing here, through the bonds, stabilizes the negative charge that's here. Now, bromine is less electronegative than chlorine, and you'll notice that the pKa is 2.81, and fluorine is more electronegative than all of these, and so the pKa is 2.66. So the more electronegative the atom is that's attached to the acidic functional group, so it's not necessarily right on it, but it can be attached on the acidic functional group, the more electronegative the atom, the stronger the acid becomes because of this inductive spreading out of the charge that's created when the proton leaves. Well, there's a distance effect that this is related to as well. So here's a series of structures in which all they did was take the bromine from being next to it, there's 2.97, and then moved it further and further away. And what you'll notice is this is 2.97, this is 4, this is 4.59, and this is 4.71. And if you remember, acetic acid and its the carboxylic acid family is right around this value of 2.78, 2.8, that rate, or 4.7, 4.8. And so this is approaching that of a normal carboxylic acid. But again, it's an inductive effect, and the inductive effect depends on how close the group is to the acidic functional group. Finally, there's hybridization. This is the newest of the ideas that we've presented to you. In Chapter 1, we talked about hybridization, and for those of you in 3A, that was a new idea. But we'll notice that if it's sp hybridized, it's going to have more S. This is 50% S, and this is 25% S. That is 1 part s orbital, 3 parts p orbital, so a total of 4 parts, and the s orbital is 1/4 of that, or 25%. So it turns out s orbitals are better at stabilizing electrons in their orbitals because they're closer, their shape puts them closer to the nucleus. And again, the charge of the nucleus is very important in stabilizing negative charge. So when it's 50% S character is what we say, it's better at stabilizing negative charge. So there's 3 structures that we're showing here. This is ethyne. If you're drawing out the Lewis structure, instead of doing a structural thing that they're doing, showing you there, you would have this. Oops, sorry, I forgot my carbon. All right, and then for ethene, or known as ethylene in common nomenclature, you would have this. Okay. Again, 2 groups on this carbon make it sp. 3 groups on this carbon make it sp2, and then likewise the last one in ethane will be sp3. When you look at if you remove the proton and leave the electrons, that is, you treat acetylene or ethine as an acid, what you're left with is this. And there's a negative charge, and something, we don't know what in this case, took the hydrogen and left the negative charge behind. That's this electrostatic potential map right here. Now there's not delocalization like you have necessarily for acetic acid, for example. But this charge is less dense than the charge that you see here, the bright red here and the bright red here. Now this difference you can't see too much of. But the result is because the charge is better spread on this ethine anion, this tends to be the most stable, and the most stable base is the strongest acid. Now, these aren't strong acids in the terms that we've come to know from before. This pKa is 25, whereas this pKa is 60. So these are all, in general, fairly weak, but there's some interesting things you can do with ethine because this is acidic enough that you can remove it with a number of common reagents. So just to review real quickly, left to right on the periodic table, right? Electronegativity increases and acidity increases. On the vertical in the group, right? Size increases, acidity increases. Larger, spread out, more charge. Here, the nuclear charge is more positive, and that stabilizes the negative charge. So electronegativity and size, these are atom effects. So that's the A of our REO, right? That's my A. And then, there's resonance or electron delocalization. So this is the R of the REO. Right? The ability to spread the charge out onto multiple atoms because of resonance means that the base is more stable, or it's a weaker base. The base is more stable, and as a result the acid is stronger because the proton can leave more easily. The lack of resonance means that its base is less stable, makes it a stronger base, wants that proton back, and as a result the acid ends up being weaker. Inductive effect, there's two things to consider in the inductive effect. One is the electronegativity if the group is the same distance from the acidic functional group, the OH in this case. Then the electronegativity is what's important, and the most electronegative, just like in atom size, the most electronegative, atom electronegativity. The most electronegative atom produces the strongest acid. And if you're looking at the same electronegative group, then it's the distance from the acid functional group that determines how strong the acid is. And finally, it's the orbital effect, that is the hybridization, and this is the O of the REO. If it has two groups on it, it's sp hybridized, and the atom's the same, like it's carbon, then it'll be more electronegative, and as a result produces the strongest acid. Now, one last thing to sort of summarize the REO. When you're looking at effects and trying to determine which acids are stronger than the other, REO is in order of importance. So atom, resonance, induction, and orbitals. So if you have an atom effect or a resonance effect, so bonded to an oxygen versus bonded to a nitrogen, then the atom effect is more important than the resonance effect generally, assuming the structures are the same and there's resonance. The atom effect is more important. And then induction is generally more important than orbital. So that's the end of this chapter 2, and we'll pick up the lectures in chapter 3. We'll try to have all of this lecture material covered in your homework and stuff by the end of the first week, or maybe into the beginning of the second week.